having us, and thank you for the introduction. We're happy to be here and excited to share with you guys a lot of new features that we've shipped in the past 3 months regarding Arbiter that I think are huge improvements to its capabilities, but also improve the ease of use. So I think it's easier to use Arbiter now than it has been ever before. And we're excited to continue pushing on that frontier. So getting right into it, about 6 months ago, we had a slide that looked kind of like this. And some of the main features I want to talk about that we've shipped in Q4 here that land us where we are now, which I would consider is stable in some sense. And some of these events include we can streamline and log events to CSV files from simulations, which is pretty nice if you want to do any sort of analysis or logging behavior over a larger amount of data. So for context, the quantity of events that you'll generate in a simulation will be relatively high, maybe on the order of thousands or more. And so when you generate a lot of data very quickly with EVM parity, you want to be able to access that data and do processing and analysis in a way that's easy. So we shipped a feature for this, which Colin's going to demo a little bit. We also got a lot of feedback on asking us to support forking features. And so lo and behold, we now have forking features, and I'm going to give you guys a little bit of a demo on how to use that and what that looks like. And then 2 other features we have. One is the environment builder. We migrated the kind of environment to the builder pattern, which substantially reduced the lines of code needed to get started and create an environment within Arbiter. And I'm going to show you guys how easy it is to do that. And then the last feature, which was actually probably the biggest feature as far as like an engineering lift, was implementing this Ethers RS middleware around our in-memory revm instance. Now, you might hear that and you might be like, wow, what does that mean? And that's fair. But at a high level, what that means is if you've used the Ethers RS ecosystem, you may be familiar that when you send a call using Ethers RS to a node, you do it with something called this middleware object. And we essentially have built the same trait. We've implemented the middleware trait for our middleware object, allowing you to use the Ethers RS API when communicating to your in-memory revm instance. So it's the same API as if you were talking to an Ethereum node, but now you're talking to your in-memory instance, and it's really fast. Some features we have planned in the next quarter and beyond are going to be a variety of plugins, and these plugins in particular are going to be related to different types of tooling within the simulation, particularly around agent tooling and post-processing and analysis tooling. We're also staying up to date with the developments with Alloy, which is the Ethers RS rewrite, and will continue to stay on top of being up to date and integrating the Alloy improvements as they come out. So moving in at a high level, what is Arbiter? If you haven't heard about it or seen it before, it's a tool for testing mechanism security and performance with mainnet bytecode parity. And we actually primarily built this tool for us to use, but we also wanted to build it in public because we saw that there was a gap in the open source tooling. And the gap particularly that we saw is that existing tools compromise on one of two things, these things being EVM parity or speed. Well, the tools that we found existing before we built Arbiter only had one of these, not both. Now, we also found that the reason this tooling is important is because there's kind of this gap or challenge in auditing risk and doing financial analysis. And some examples of this might be is like who should provide liquidity, do what, and with what expectations. And I think that these types of questions in this context can be answered with a high degree of granularity with tools like Arbiter, which is pretty exciting. And also at any time during my presentation, I'm happy to be interrupted and answer questions. So I just want to put that out there. So moving in, the largest changes we made are the middleware changes. And so, as I said, we implemented these middleware traits from the Ethers RS middleware module. This allows us to have the same API as Ethers RS middleware while maintaining our speed as using revm as our under the hood execution engine. And it also means that if you have an agent that interacts with any contracts in your simulation, the logic for how they interact with it is actually identical to the logic with how they would interact with it on mainnet. It's as simple as just switching out your middleware. This makes the interface here modular and familiar to the rest of the Ethereum ecosystem. And under the hood, how this works is the middleware object that we have, it communicates to the module we have built called the environment across some channels. And I'm happy to walk through some of that code today, actually. Another thing we recently shipped in our minor version 6 release of the Arbiter core library is support for environment cheat codes. If you've used Foundry before, maybe you're familiar with some of their cheat codes. We are shipping a variety of these as they are needed. And so far we have shipped some of the environment cheat codes, which is exciting and has proven useful. Now, here's a little bit of a summarization of the environment builder and what it looked like in the past. So this right here is a code snippet of the code that you had to write in order to build in-memory revm environment and then some middleware around that environment. So it went from about 22 lines of code right here to now just 2 lines of code to do after adding Arbiter core to your TOML and using the environment builder and the revm middleware is these 2 lines of code. With these 2 lines of code, you have a client with a signer that you can deploy contracts with, sign transactions with, make state mutating and non-state mutating calls to the in-memory revm instance. So we're really excited about this. I think this reduces the user complexity a ton and the barrier to entry to using a tool like Arbiter. Now, another tool that is really exciting is we recently shipped a feature around event capture. And what this does is it automatically logs events to CSV files over the course of a simulation. And Colin's going to do a demo on this a little bit later, so you guys will be able to see this in action. And so you can gather, thousands of events and log them to a CSV in a matter of seconds. So how this would look and what the end user API looks like for this is here you can see we have the two lines of our environment and our client with Sire. And in practice, I wrote a comment here. There would be 3 contracts that the client would deploy prior. You'd just deploy a contract named arbx, arby, and lex. What these names are for us is in some of our testing, we have a ERC token, ERC20 token, we just call arbx and ry. So these are just token contracts. And then the lex contract is a contract that whose bindings ship with Arbiter, that is this liquid exchange contract that if you want to model stochastic price processes with, it's helpful. And so here we can see we're creating this listener, and what this listener is doing, what we're doing here is we're setting an output path, and we're saying, hey, log all of the events from the arbx contract, from the arby contract, and from the lex contract. And let's title these events in the CSV arbx, arby, and lex. And now when you run your simulation, these events are going to be logged to the CSV. So this is another really exciting feature that we're excited about and we think brings a lot of visibility to on-chain activity and examining the behavior of not just smart contracts, but systems of smart contracts. So that's very exciting. So real quick, I'm going to give a brief overview of the repository. With the middleware upgrade, which was pretty big, we consolidated down from 4 crates to 2 crates. And so if you're familiar with the Rust ecosystem, there are 2 types of crates you can have, and we have exactly one of each here. We have a library crate, which you can use to access any of these abstractions and tools that we've built. And then we have a binary crate, which is a command line interface for Arbiter, which is what supports some of the forking features, some ways to generate bindings, and we also have like an initialization to create a new Arbiter project in the binary. Now, both of these are on crates.io, so you can simply cargo install Arbiter to get this. So it should be super easy, and it should, if you want to use the library, it's as easy as saying adding Arbiter core to your COML. So this is pretty nice. Now, with that, we're going to dive into the code. Now, before I do, I'm going to grab a sip of water, and if there's any questions so far, feel free to shoot them at me, because we're about to get into the guts of Arbiter. Okay, if there's no questions, that's totally fine. What I'm actually going to do first is I'm just going to open up a terminal instance here, and I'm going to walk you guys all through how we would make this a little bigger so that everybody can see. Can you guys see my terminal okay?
Yep.
Cool. So if I were wanting to get started with Arbiter, what I would first do if I was using Rust and I had Cargo and Rust installed, I would just do Cargo install Arbiter like this. And as you can see, I already have it installed. But if I didn't, Cargo would install this binary for me, which is pretty nice. Next thing I'll do is I'm going to use the init command to create a new Rust project with Arbiter. And I can name it something silly, you know. And what this is going to do is it's going to clone a template, very similar, actually exactly the same way that Foundry clones template. And I'm going to go into my project, and let's take a look actually of what's going on here. You guys see, can you guys still see everything okay?
You're good.
Awesome. So as we can see, we get some stuff here. The contract we have here is just this counter.sol. So really simple counter contract. You've all seen this contract a million times. We don't need to talk about it too much. We have this fork example, which I'll demo in just a moment and talk a little bit more to show you guys how to use the forking feature. Then there's a lib giving us the forge standard dependencies, an out. A lot of this is very similar to Foundry contracts, a script. But here, the source is where I'm actually going to be interested and spend most of our time. So in here, there's a module called bindings, which has the counter Rust contract bindings. Under the hood, these are generated with forge bind. However, we've built a wrapper around it so that they're always output to the same directory. And we have worked to kind of eliminate the friction between working with Solidity and working with Rust. And a key friction point here is how these bindings are generated. And to be frank, I think there's still some things we can do to smooth out this process more. And it's something we're actively thinking about and trying to do. But what this means is if you make changes to your contract, you have to run Arbiter bind to have the updated contract bindings when interfacing with them through Rust. Now, let's take a look at our main here. I have a very simple binary here. I introduce a few dependencies. A lot of this is just from Arbiter core and some standard stuff. And then I have this main binary right here. And right now it runs this counter example. And right now what this counter example does is it has these two lines. It gets us our in-memory revm instance and then an EOA with some middleware. We log the account address. Then we deploy the counter contract, log the counter address, and then we increment. And actually, I'm just going to real quick make this like 10,000 just to demonstrate the speed here. So we'll increment the counter 10,000 times. And then we'll do a call just to read the counter variable to show that it has been incremented appropriately. So I'm going to run this real quick, just with cargo run. We're going to wait for the compiler to build since we haven't compiled this project yet. It's new, it's fresh. I probably should have built it one time while I was talking. But no worries, we're still gonna get there. The Rust compiler is our friend. And so as you can see, we incremented the counter like 10,000 times very, very, very quickly. Like the whole thing ran in, I don't know, maybe 1 second, maybe 2 seconds, I don't know. So that's 10,000 state mutating calls in a very short period of time. So you can imagine the kind of power that this would leverage you to build different environments, to stress test different contracts in a number of ways. So now what I'm going to do is we're going to comment this out, and we're going to look in a demo of the forking capabilities. So let's take a look in this fork example. What's going on here is I have this wet fork config toml. And there are a couple fields in here that you configure that define what fields you want to fork when you are using this. Now, I already have this forked state in this test.json. So what I'm going to do is I'm just going to rename this output file new test.json. And so our state's going to get queried from an RPC, and we're going to log the output to fork example new test.json. This is the block number we're grabbing from. This is the externally owned account that we're grabbing from. This is just Vitalik's account. And then these are the contracts and their metadata that we're going to grab. So when you're forking a contract, you do need this artifact of the contract because it has some information regarding the storage layout. So let's run this. The way you would run this is you would run the Arbiter binary with the fork command, and what you pass it is just a path to the config. So what it's doing is it's grabbing all of the storage for the web contract. Right now, we only store storage mappings, one map deep. For nested maps, is probably a feature we'll ship sometime in the future here. But right now, it's just one deep. So as you can see, we get our new test JSON. Now let's head back over to our main real quick, and let's look at how we would load this into an instance of our revm middleware so that we can now play with this forked state in our super fast EVM sandbox. So the way that this works is we load in this fork object and we pass it the path. Now, real quick, I need to give it the new test one because we just changed the output path. Otherwise, it would have done on the old test, which for the sake of the example, maybe makes sense, but in practice, they're exactly the same. So we're loading in the fork from the fork path. We're, of course, creating our environment, but now what we're doing is we're building it from the forked database. Right now, this is an example of how to use the forked EOA. And what we do is we actually have this new from forked EOA method on the revm middleware that still takes in an environment and then a fork address. But what's cool now is now I have like God mode over the value, the account, the EOA, Vitalik's EOA. So now I can actually, deploy a transaction as Vitalik, for example. and sign transactions as Vitalik, and now my forked instance. So let's run that real quick just to see that go. So as we can see, we're reading our new fork DB. We can see that, Vitalik deployed the WETH contract. So we basically kind of have God mode now in our fork version of Vitalik. And we can say, he has this much ETH as well, just to show that the state that we grabbed does have state and is working. Now, the last example I want to show you real quick is an example pertaining to the forked contract state of the WETH address. And it's very similar. The first few lines are the same, except now we don't actually really care about the Vitalik's EOA. Instead, what we're doing right here is how historically we were deploying WETH. Now we're just saying, hey, just create a new middleware instance to the WETH contract, passing it the address. So if we, have a contract that is already deployed in our in-memory EVM DB, we don't have to create an interface around that contract with the deploy. We can just use this new instead. And then to show that we grabbed the right contract state, what we're doing here is we're just, getting the balance of this specific address. And what we're doing right here is we're in the fork config, we put this balance of. So this is some memory we specifically have specified to get. And so what we can do is we can check the balance of this address, and this is Vitalik's EOA as well. And then we can make a real balance of call to the WETH address to show that we did in fact grab the contract state. So let's run this real quick. So we can see we got the address, and there is some, non-zero state for the balance of Vitalik's address in this contract, which, shows us that we have successfully forked the storage state of this contract from mainnet and then loaded it into our in-memory instance of revm, where we can do more performant actions and stress testing against that. So overall, this forking feature was something that was highly requested of this, and we're excited that we have it now. And I think that it makes grabbing contract state from mainnet a lot easier. So you can just grab whatever contract state you want and then load it into the in-memory revm DB. Important to note, you do need the contract artifacts for the deployed contracts, because they have some information about the storage layout. But that wraps up the demos I wanted to show you guys on, one, kind of the speed, two, the how to use the CLI with the bind command, as well as the forking command. And then the next thing I would like to show you guys is a little bit of an overview of the middleware in the Arbiter core repository, show you guys how it works. And I would also like to hand it off briefly to Colin to demo some of the event capture capabilities. I'm thinking let's do that first, actually. Colin, are you ready?
I am ready. Can you guys all see my screen? Should be a mirror of what was being shared. We're good. Okay, nice. So what I want to show you real quick is a little bit, of a project in-house at Primitive. So I'm not going to show you everything we're doing, but I can, imagine you might find Easter eggs on this page here. And I can give you some of the ideology of like what we're going for. So the other protocol, or I guess the protocol we're working with at Primitive is called Portfolio. And we want to do some like portfolio management strategies with it. So with that, we've built sort of an apparatus around Arbiter Core that's letting us do our testing in, one contained environment that we are iterating on, and we'll bring features from and put them into Arbiter or Arbiter Core as necessary. So supposing you can see my screen, someone yell at me if you cannot. On the right, you can see what I have is just this config. This config file is kind of the setup for a simulation, running like a dynamic weight simulation. So think balancer style AMM, where I can change the weights of two assets in a pool. So maybe I'll start with like a 50-50 weight. This would be like Uniswap v2. And maybe I want to do something like have my pool have some sort of target volatility. So in this case, we're going to set that to be 15% year over year target volatility. Anyway, what I'm doing in here is setting up some config stuff, maybe sweeping over different parameters if I want. For the moment, I'm just going to run 10 simulations with a fixed volatility, fixed drift for my price process, and run it 10,000 times. So 10 times 10,000 times, we'll do, 5 times 10,000, we'll do 50,000 steps. Our project is called Excalibur. So I'm going to use our simulate command and run this config I'm showing you with a little extra verbosity so you can just see what's going on. So we start up these 5 simulations. At the moment, I'm going to run 2 of them in parallel. We hope to get this working with as many as you want in parallel. So at some point, we will have that. Nonetheless, this will finish here in just a second. So we ran these 5 simulations, 50,000 steps in about 16 seconds. There was a lot going on in those simulations. We could see what happened, right? So all of that data I wanted got captured over here, and it came out in this file, static volatilities. Now I have some extra stuff in here because I've been, running other simulations, but nonetheless, I believe the one we were doing was this. Here's a bunch of trajectories. Inside of these, we have our CSVs that automatically logged events for us. And if we want to take a look, we can, see all the data that comes out in these things. But reading CSVs with your eyes is not really a fun task. Instead, I want to show you that, this data can be useful in kind of understanding, what's going on with your contract or how is your strategy performing. So we also have the ability to just say, let's take these weights and look at like how they behave statistically over time. So since we did 5 different price paths here, we can get a little bit of statistics and take a look at like how the weights evolved over time. So just looking at this sort of graph, what we did here is we plot the mean of the weights from each of the 5 different simulations. Those are the dark shaded lines, the orange and blue respectively. And then what the sort of like area around this represents is the standard deviation of those weights. So since we have multiple trials, we're going to get some deviation from the mean. And we're just seeing that these weights do start to approach something like, 0.85, but there's this kind of like band of deviation around them. So nonetheless, just wanted to show you, when you go about doing these simulations, what's nice is automatically capturing all this event data that you want. Maybe it even teaches you or tells you that you should be logging something here, or maybe adding additional logs just for your simulations. At any rate, you can take this sort of stuff. It's in a nice format for you to just go ahead and do some kind of post-processing. And hopefully at some point in the future, we also just give you the ability to have some like native post-processing tools. Not quite shipped at the moment, but something we're definitely working on getting to you all. So that's the demo I have. Feel free to ask questions if you want now, or we can talk about it more later. But I'll hand it back to Jepson for now.
Nice. That was really good. give people like 2 minutes to decide if they want to ask questions on that.
I have a question.
Yeah.
Hi, I'm Dylan. I'm with Delve. I was curious how, maybe you said this, I apologize if I missed it, but how are you storing that event data? Is that like in some sort of database, or like how is that information being stored?
Yeah, good question. So in this case, that was stored in a CSV. So CSV we saw as like a simple way to get started, right? And moving forward, we're probably going to change this to be maybe something more robust, something maybe a bit easier accessible and easier to like parse. But for now, it's just CSV.
Maybe. Okay, yeah, you did show that. So, if I'm running something that's going for a very long time, it's just going to make one giant CSV file. Is that right?
Yeah, one for each event. Yeah. So you'll get like a different CSV for different events. So okay. I don't have my screen shared again, but like we had a weights, like a weight change filter, which was like the weight changing event. And then we also had like a price change filter, for example, right? So like these would be stored in different CSVs. And again, we hope to make like a better structure for this, but we saw this as a very natural stepping stone and a good way to just like make this sort of behavior automatic for people and, get rid of that hiccup of like having to actually set up some kind of like data output for yourself.
Yeah, makes sense. Thanks a lot.
Of course.
Forgive me if I missed it, but I'm not sure if either you, Waylon or Colin, if you showed the API for the event logger. It's like pretty straightforward for just like picking which events you want to.
Yeah, let me go back to it actually.
Thanks for bringing that
So
up.
this is the API. So all you got to do is just, use this add on this event logger builder. So if you have a new event you want, you throw it in here. And Dylan, you actually asked kind of a good question because we are currently cooking on ways to even improve this feature further. One, so that it's fast and performant, but two, so that the data is more unified and post-processing is easier. So, keep your eyes peeled. We'll be continuing to improve upon everything we've showed you today, as we have since our last meeting too. But with that, there's one more piece of code I want to show you guys, which is the Arbiter core code. You guys able to see my screen okay? I'm going to assume yes.
Yeah.
Now we can see it.
Nice. Okay, great. So this is the Arbiter repository. You can, find this on GitHub. It's all open source. If you want a feature, open an issue. If you have feedback, let us know. We're super eager to hear from you on how you're using Arbiter and how we can improve it to make it easier for you to use. But in this Arbiter core repository, this is where our kind of the meat of Arbiter lives. And I'd say that the in this library, the two modules that I think are the most critical or have the majority of the functionality are in this middleware module and this environment module. And I just wanted to give you guys a rough high-level overview of under the hood, what's actually happening when you're creating this middleware instance and this environment instance. Now, what's going on between these two is the environment is basically like an object that is always listening to any middleware that is created around that environment and processing any transactions that those externally owned accounts have created through that middleware object. So I would say that this is probably maybe the scariest part of Arbiter. So we're gonna get it out of the way, and then you guys don't have too much to worry about there. But as you can see, the environment struct, it has a DB. This is a Ethereum DB. So this is, you know, our key value store of the Ethereum state, right? These are our parameters. These are created with the builder pattern. This right here is what we call a socket, which is a collection of channels where we listen to EOAs through their middleware. And then this right here is the thread in which we want to run the EVM in. And so the main thing here, you guys, you know, probably not interested in constructors and whatnot. These are more elementary pieces of software. But I think what might be a little bit more interesting is this run method, because this is kind of where all of the logic happens, where we are, you know, actually incrementing the state using revm and processing transactions with EVM parity. So of course, we have our EVM object, and this, if you want to learn more about this, this is a package that is core dependency to Arbiter revm. Take a look at revm. Revm's great. It's become critical infrastructure in Reth and a lot of the rest of Ethereum ecosystem. We take in some configurations. We have two hard-coded configurations right here. We set the limit contract code size. This is, I think, a little bit bigger than what it actually is. And then we set the gas limit of blocks to be the maximum. So we want to just kind of churn through things. And we have some ways that we allow people to model block space with here. That's actually right in the next few lines. So we can get right into that. What we allow people to do is configure some block settings. And there are kind of two configurations that we allow people to configure if they want. And if you want to use this, you just use the builder pattern on the environment at the end user API. Very simple. But the block settings that you can configure is you can have this randomly sampled configuration in which you pass a block rate, a block time, and a seed. Or you can have a user-controlled configuration in which you pass none of this. Now, what's going on here is we're actually creating a Poisson distribution with the block rate as the rate parameter and the block time as the time parameter with a seed. And the reason a seed is very important in simulations is because reproducibility is critical. Say you're running, 100,000 iterations on some smart contract system, you're gonna want to be able to reproduce something if you find some sort of anomaly behavior. And in order to be able to do that, you need to control your seeds or your sources of randomness. So there's this. We actually do something a little bit similar here with gas settings. So we can, have this these randomly sampled gas settings, in which case, we can create some heuristics to model the gas prices. Now, I think an improvement on this would be, just implementing EIP 1153 directly, and perhaps that's something we'll do in the future. But we do support some ways in which we allow people to configure these heuristics to tune their simulations. So for the gas settings here, we have user controlled, so we can just allow the simulation designer to set the gas price whenever they want. In the same way, we can allow them to increment the block whenever they want in their simulation. This is the user controlled configuration. We have this randomly sampled gas setting, in which case we can basically anticipate an amount of transactions per block on average that we want to expect using the Poisson process. And then based on what the sampling of that process is, we will, once these amount of transactions per block has passed, we will increment the block and go from there. And then we also allow a constant gas price. So now we, kind of create some now the insurance we have is we can add an account. This will open the key value store of the account. These accounts can be ETHs or they can be contracts. But we'll sort an account into the EVM DB with the address and the account information. We also have this block update instruction, which, if you're using the user controlled block configurations, you can send this at any point through your simulation loops. If you want to increment the block on some heuristics that you would like to define. We have the code, environment cheat code. So, for example, we have load. If you want to grab the account and keep. Right now, we don't index this on a block. Perhaps that's a feature we will ship soon in the future, or if it's something that's very useful to you, by all means, come on in. We'd love to have you down in the trenches with us. We also have store. So this is, adding a value to an account's key values pair. We have deal, which is kind of giving an EOA a bunch of ETH. And then we have our call instructions. Now, our call instruction is non-state mutating, but of course we support non-state mutating calls because that's an important part of how Ethereum works. We also have the set gas price instruction. If you're doing user-controlled gas prices, we allow you to set that if you want to define the heuristics yourself on how you want to do that. And then we, of course, have state mutating transactions as well. And this right here, other than these queries, which are kind of information queries, so our environment is just listening to all of these types of instructions it can receive. And when it receives them, it then executes the right instructions on the EVM DB using revm, which will then, take your call data, turn it into the bytecode, and on the revm stacking. And on the other end of these sockets is the middleware. So we can take a look at that. So the middleware object right now is just this provider that has this and this wallet, this externally owned account. Now, how we support having like the ability to sign transactions from Vitalik's forked account in like a simulation is we can kind of create these like under the hood mocked or like forked EOAs, in which we kind of bypass the signing authentication. But other just regular legitimate wallet objects if we're not creating them from forks. So we implement a lot of things on the middleware, but at the end of the day, if you are familiar with the Ethers RS middleware traits, what we're doing here is we're just implementing these traits for our revm middleware object, right? And so we're writing the logic here of how we want this API to that Rust Ethereum developers are familiar with, how we want this logic to behave under the hood. And so what we do is we connect it to our environment and give the responses that it would expect from the environment. So of course, in some of this, here is, I want to go select timestamp, I can do client.update block, right? And this will then send that block update instruction to the middleware. If I want to do some reads, maybe I want to get the block timestamp, maybe I want to apply a specific code and pass in one of these cheat code enums. I can just want to know the address of EOA. If I want to set the gas price, these are end user APIs on the revm middleware object. Yeah.
Just a quick heads up, your audio is cutting out a little bit, and just a quick time check. You have about 8 to 10 minutes. We can go a little bit over, no worries, but just to leave some time for Q&A as well. I think some folks had some questions.
Yeah.
So feel free to wrap up.
Sorry about the audio. No Hopefully worries. Yeah. Hopefully this is okay. Maybe I'll skip the rest of this for now and hop right back to the slides since we're coming up on time. I have, I think, one more slide that I wanted to talk about, and then we can open it up to questions. So moving right along, here are some latest benchmarks. These were done 2 days ago, so these are up to date on the latest version, even the patch version on version 0.6.3. So this is the relative performance difference when comparing the speed of revm to Anvil. And this is pretty substantial. Now, I want to talk about a little bit why this is. So the way that Anvil forks mainnet is it maintains an RPC connection to some Ethereum nodes. And if you are executing a transaction on a Anvil fork, what it will do is it will check its cache and see if it has information. And if it does, it'll process to query that information from mainnet. So Anvil's pretty dynamic in the way it responds to the user's demands when it's offering its forking functionality. And to be honest, this is a great feature that they went on. But the trade-offs of this feature is that it cannot be as fast. So you saw a little bit in our demo, the way that we've decided to go about approaching forking is allowing users to define some heuristics in the fork config to fork the mainnet state once in the beginning and then load that fork state into your simulation environment so you can still have all of the speed. So this is the trade-off that we went with that allows us to maintain these performance multipliers, which we are quite happy with and proud of. Now, the last two things I wanted to touch on, if you guys want to stay up on doing at Primitive and how things are going, check out our blog. We write kind of a detailed change log. We've been doing this every minor release where we talk about the issues that we're closing and why we, shipped these features and how we shipped these features. If you want, to follow us there, feel free. Also, we're on crates, so should be pretty easy for us to integrate with you if you're familiar with the Rust Ethereum ecosystem. And, the last thing I want to say is that the community is really important to us, and the feedback that the community has from using a tool like this and how to make it better and deliver the features to the community that they desire is something that is important to us. And so we're always excited to hear from you guys. If you guys have questions or comments or demands, feel free to reach out to Colin and I. We're core maintainers of Arbiter, or even anybody else on the Primitive team. We have a Telegram group chat, or, we're pretty friendly if you want to talk to us. And with that, I'll leave it for questions.
Yeah, I think some folks had some stuff in the chat. I believe Colin already answered some, but Colin or Jepson, if you see anything that hasn't been answered, or if anybody wants to speak up or ask new questions, please feel free. We can run Q&A for about, let's say 10 minutes or so. So yeah, if anybody has anything, please feel free to speak up or drop it in the chat.
Yeah, feel free to unmic yourself. Yeah, go for it. What's going on? How you doing?
Hey, good. Thanks a lot for this, you guys. This is really impressive. I love it. But I was wondering, is there any control over the over like mining, like Anvil has? So if I'm running a simulation, I might want several agents to test sand fatigue type of things. So yeah, what do you have there?
Could you? I don't know if I understand the question exactly. Are you talking about like ways in which you would want to like pause the environment, or could you say a little more?
Yeah. I'm just wondering if you could control how the blocks are mined. So are they auto mined for connection, or can you manually work all those things?
Totally, yeah. So I was going over this a little bit in Arbiter Core, but what you can do is you can predefine some heuristics if you want to have like Poisson processes. So like Poisson processes are very good for controlling, frequency of occurrence types of phenomena. So if you want a block on average to happen after X amount of transactions, you can figure that within the random distribution block settings. Now, what we also enabled is a fine degree of granularity over how you want to control your block settings and how frequently you want blocks to come, by also just allowing this to be user controlled. And so an example of how you would want to use this if you want to define your own heuristics is you would make one EOA that would be like an admin EOA, and you would have them increment the block on, whatever heuristics that you define. So right now, these are the two options for controlling the block heuristics within revm. One, the user has full control. The other is used to model or to block rate frequency that you're able to define. Does that answer that question? Yeah, go ahead, Colin.
I was just going to say the simulation I showed you, we use an agent that after some amount of time or amount of like transactions that go through, updates the block and increments the block timestamp as well.
Cool. Yeah, that answered it.
Great. Colin, were there any questions that were asked over chat that you answered already that you think would be worth sharing?
Yeah, let me scroll back through it. There was a good discussion about like data storage. So worth going back through and reading that for everybody. Then some ask about our Excalibur project.
Yeah, would you mind summarizing the data storage conversation purely for the audio listeners? So we will be posting this as well. So they won't have access. So if you don't mind, I think that would be great. And then you can lead into Excalibur.
Absolutely. Yeah, so I kind of posed this question as we were talking about it because we're planning to work on it today, actually. But we have our current like event capturing system just like output the CSV. So I posed this question of like to you all really, that is CSV the output that you would want? And so we got some suggestions for, using like Postgres, like using like a real database, right? To like output all of this stuff into. Teammate of ours was talking about Parquet and KV Store in general, like SLED. And I also just asked again, like, do you all think even like this sort of columnar data storage like system, so like maybe CSV or Parquet, like, is this the right approach? What do you all think? So looking forward to hearing back from all of you and like what you would like to use for this. And, we're happy to hear all the suggestions and have a good discussion on that because we just want to do what we think works well for everybody, even if it means, just providing more optionality for how you want your data to come out. That's also a feature we're, happy to ship or work with people on shipping. I think some of the other questions too, just reading through it, one of the other ones was like, what explains the speed difference between our revm middleware and Anvil? A good portion of it comes from the fact that we don't do any sort of like networking style communication, no HTTP or WebSocket. Everything is done via like channels in Rust, which, you can think of as kind of like, transmitting over a wire, although effectively it's just like this sort of wrapper around like owning the same vector and just like placing something in a vector and letting someone else own it. So it's a very fast way of doing communication, or at least what feels like communication from the outside world, communicating into the revm execution environment. I think this is what gives us a lot of the speed over like, say, the stateless calls and things like this that have, say, like a 10 to 30x speed up. The thing that gave us like the 75x, or even at one point, like over 100x before we had like a gas inspector, was on the stateful calls that are like state mutating calls. The difference between us and Anvil is like truly mining blocks and then outputting blocks, that are stored so that you could go fetch a block by like a block hash. We are not doing this process. So if that's something that you need, then what we're hoping to have for you is still the ability to create environments that, say, use Anvil as an execution layer and give you the tooling and everything around it, such that if the features such as forking that Anvil does, or having like true blocks formed is something that you want, then you can use that. But if speed is your pure desire and you just want to like really stress test something or get a lot of data, then the environment that we have currently set up is probably the one you would want. So there's trade-offs there, but yeah, they come for a reason.
Yeah, both Anvil and the revm middleware, we are processing real EVM bytecode, one abstraction lower on a real EVM execution environment. So the bytecode parity, I think, is something that's cool and important. And like we said in the past, we saw that existing tools either had EVM bytecode parity, or were fast, not both. And so we decided to go in that direction.
Yeah, just for clarity, Anvil uses revm. So at like some end, the actual execution of bytecode is going to be the same speed too.
Yeah, it's identical execution of bytecode.
Okay, so it's fair to say then that the revm middleware here is kind of doing all the block actions except for not creating the actual block. So I guess another way to say that it processes a number of transactions in a quote unquote block and then just like updates state and then moves on.
So what we actually do is right now we don't have a notion of pending transactions at all. Like revm very raw is just a stack machine. So as our environment receives instructions, it processes them immediately and updates the state through the stack machine. But you bring up a good point, and we have talked about this internally of, introducing the notion of pending transactions in this toolkit and what trade-offs that would assume and what features it would enable and how important are those features.
Yeah, it would be amazing to have at least a little. Yeah, exactly. Yeah, create your own mempool that's still like super fast. It just accepts like, I guess you can configure it to, between 50 and 100 transactions, whatever, some random amount, so it still goes fast. Yeah, I'd love to help. And yeah, and exactly, yeah, and because like sandwich attacks are kind of like a big thing, right? So that would help be able to test those kinds of things.
Yeah, absolutely. I think it's a great idea. I'd love to hear more of your thoughts, either in some issues on the repo or in the Telegram. Come chat with us.
Awesome, guys. I think we're coming up on time. But yeah, for Colin and Jepson, thank you guys so much for the fantastic presentation. For everybody else, if you have more questions or if you'd like to engage with the folks that are building Arbiter, such as Colin or Jepson, please feel free to reach out on the socials that they mentioned. And guys, if you want to drop your socials or the relevant Telegram group inside of the Spearpit Discord in general, please feel free to do so. Also, feel free to drop it inside of the chat message inside this voice channel. But yeah, if you guys want to, Colin and Jepson are both in the Discord of Spearbit. Please feel free to DM them. I think you guys shouldn't have any issues. They're both extremely friendly and very responsive. But yeah, thank you guys so much. And yeah, if you guys do you guys have anything else that you'd like to say to the community, or otherwise we can go ahead and close out?
Yeah, I mean, the last thing I would say is we just really want this project to be things that everybody wants to use. And we put our own ideas into it. But, we're a smaller team with a goal in mind of our own that is going to be different from all of yours. If you have ideas, we'd love to see them. We would love for you to share them. We're happy to help you with it, happy to help you get to know the code base, and just happy to help you get going on your own simulations. That way you can test your protocols, test your strategies, or whatever you want to do. Just reach out to us. We're more than happy to help out.
Awesome. Well, fantastic. I think that's all we have time for today. But again, thank you both so much, and everybody have a great rest of your day.